Hello to everybody. Nice to be part of such an important and special meeting. I would like to send over the floor to Mr. Professor Kaynia. He is a technical specialist at Nor Consult AS and professor at the Norwegian University of Science and Technology. He is a distinguished researcher and a distinguished project leader. He has led numerous keynote lectures. He has wrote numerous papers, peer-reviewed papers, and coordinated several national as well as international research projects. So he will give us explanations on part 5.2, application to geotechnical structures, site stability, and liquefaction. Please be aware the speech to take somehow 25 minutes, so we will have 10 minutes last for questions. Thank you very much.
Thank you very much for the introduction, Professor Kober, and good morning, everyone. I'm going to talk about section 7, evaluation of the seismic response of the construction site. 5 topics are included in this chapter. Siting, potentially active seismic faults is the important one. Slope stability, potentially liquefiable soil, settlements of soil under cyclic loading, and ground response analysis, GRA. Actually, the first 4 are the same as the one, those in the current one, 2004 version. So what I could say, I could add also these 2 ones, and there are 2, and then I could add discussion. There are 2 associated annexes, only informative. Annex B is procedure for liquefaction analysis, and Annex C is for evaluation of settlement. What I can say, like overall, is that version 2021 is basically keeping the skeleton of these 4 topics, these 4 sections from 2004. However, what I could say broadly is that it's more detailed. There is more clarity. Of course, it has been updated to match the principles of the new part 1. It has much more information useful from recent research, and basically covers the topics in more detail and clarity. So that I could say is the advantage of the changes. So I start with citing and look at what we have from, I'm not going to read, of course, everything. This is a copy from version 2004. And on that one, I basically, the principles, skipping the principles, we have proximity to seismic active faults, which says buildings of importance classes 2, 3, 4, then should not be constructed in the immediate vicinity of tectonic faults, and so on. But of course, it just stops at that, and then it leaves it to the designer. So this is basically, there is a major change in the new version 2021 that allows for construction close to faults. One issue is, of course, the whole concept of being active to faults, active faults, which is the hazard part of it. And this is dealt with in part 1, that what should we do if we are close? But that is the hazard part, the special seismic hazard studies and so on. Here we are talking about the foundation aspects of it. So what is then done with respect to that? Potentially active seismic faults, it says close to potentially active faults, and then says roughly a few hundred meters. Structures of consequence classes CC2 and 3 may be constructed if there is a continuous stiff foundation and if there is enough soil cover. And then there is a table, a figure provided. 3 curves are given, A, B, and C, and each of them give the thickness of the soil cover for low seismic action, moderate, and high. So one could, based on the shear wave velocity, decide what cover, soil cover is required so that one could construct. Then it goes into more detail. Bearing piles should not be designed to cross the potential fault plane, and their tip should be located at least 10 diameter above. If not required to consider, and it is not required to consider simultaneous effects of fault rupture and structural vibration due to ground shaking. This is most relevant for underground structures, as we will see later. Slope stability. The general concept is that when slope instability affects an adjacent structure, the consequence class and limit states should be taken as those for the affected structure. And limit state for slope is based on acceptable permanent ground displacement. So method of analysis, as Professor Baker explained, are the two FBA, force-based approach, and displacement-based approach. However, the force-based approach is allowed only if there is no danger of liquefaction or significant reduction of soil strength. So that means that the only possibility is a DBA. And especially the displacement-based approach is encouraged if an evaluation of displacement is needed. For example, we need certain amount of displacement with respect to a structure, so then a specific number is needed for the displacement. Otherwise, one could do most of the things with the force-based approach because as Professor Baker explained, it has been very much detailed. If I look at what is in the current version, again, I'm not going through all of it. I'm just focusing on what is the major change. Here, we are following the same principle. The response of ground should be calculated based on two methods are explained. These are the two analysis methods, FBA and DBA. So they are even not under the banner of FBA or DBA, but both are mentioned. Finite elements, pseudostatic methods. And then for the FBA, it comes through this simple expression that the horizontal acceleration, basically, it's like you take half of the seismic action and then apply it to the slope. So in the pseudostatic approach, pretty simplified, it's very easy. And this is FBA is handled in more detail and clarity in 2021 version with consideration of soil nonlinearity. Professor Baker explained it. I just add a few more description on it. The seismic demand for the slope is the same horizontal seismic coefficient. This is that AH. The acceleration is given in the same, this is explained, this was already explained, that this is actually a peak acceleration times a factor beta h and chi h divided by chi h. This is that 0.5, this is replaced by these two parameters beta h already described and chi h already described, accounting for soil nonlinearity. But now that 0.5 has been replaced with more detail beta h and chi h. And we performed some analysis, simple analysis to establish for different limit states, consequence classes, what could be these factor pH reduction factor. And it varies between 1.5, 2 and 2.5 for these seismic classes. It was based on some numerical calculations, some use of empirical methods, and for the displacement range that we set, considered like typically 6 to 10 centimeter and so on, we came across these factors. So that means that in addition to the beta H that is allowed, already there is a possibility of reducing further for displacement. And then basically, as Professor Baker mentioned, if we are changing the conditions for these limit states, we should go back and change also these pH. Vertical component is pretty much like before. It's taken half of the horizontal, And seismic resistance of the slope should be expressed by critical slope. So we have seismic demand, which is basically the acceleration used. And then we have the seismic resistance, which is in terms of the critical seismic coefficient alpha C, which is the minimum value of horizontal seismic coefficient that could lead to pseudostatic failure. So it is these two versus each other. The displacement-based approach, performance of a slope should be evaluated based on acceptable permanent displacement. Permanent displacement may be calculated using, this is similar to before, nonlinear dynamic analysis or rigid block, but rigid block cannot be used if there is a significant reduction in the soil strength. And the seismic demand is again in terms of permanent displacement, and the seismic action summary in terms of maximum displacement. Liquefaction, potentially liquefied soil. Liquefaction is pretty much the same principles, again, much expanded, and with more information from recent studies. Liquefaction should be performed for three conditions, and then there is the discussion of groundwater level. What is groundwater level should be considered. Consistent with the definition of Eurocode 0, for the groundwater, it should be based on what we call quasi-permanent value. This is a concept defined there, which is a simple definition for it would be an average for a chosen time period, or what is a dominant water level. So one does not need to consider it with a high rain season and things like that. Susceptibility to liquefaction, very well defined in an Annex B, but at a high level is defined as sand, gravel, silty sand, and fine grained soil with plasticity index not greater than 15 should be evaluated for liquefaction susceptibility, and soils with clay fraction greater than 15% are not considered liquefiable. Liquefaction assessment may be neglected for magnitude smaller than 5. This is an NDP value that can be changed. And these are one of the advantages of the current version, that there is more allowance and more relaxation for low seismic actions, and this comes more and more in different parts. For structures on foundations other than piles in low seismic action, this consequence of liquefaction can be ignored if liquefaction is found at depths greater than 50. The assessment itself is the classical way. I'm just having it for completeness and having it if the material is distributed. It's in terms of the cyclic resistance ratio, pretty much the classical way. And however, no reduction for beta H or key H. So they should be taken both one, in other words. And this is, it is an additional thing for heterogeneous soil profile, like when we have stiffness contrast more than 3, a tau max, the maximum stress, the action should be determined from a ground response analysis. CRR should be evaluated using SPT, CPT, the same as before, and a very detailed, based on the most recent established method available. It has been put in Annex B, and one is allowed to take all the permitted factors to correct for that, like earthquake magnitude, effective overburden pressure, fine context, and all the like. And Annex B is informative, very detailed, it's there. For fine-grained soil, there is actually laboratory test should be performed. And this is like a condition for how a fine-grained soil is considered. This is in an annex, is considered to be susceptible. So there is extra information, and liquefaction assessment. This is also new for low seismic. If soil is considered liquefiable, then what should we do? Low seismic action classes, then liquefaction may be assessed using a simplified liquefaction index method. This is in Annex B, which is based on this liquefaction severity index method. For moderate seismic action, then consequence of liquefaction may be assessed using a combination of simplified method and free field settlement. Then we have an Annex C that gives procedure for estimating the settlement. For high seismic action classes, potential consequences should be evaluated, and then it could be done numerically or based on numerical methods, numerically or empirical methods. And one should think about exceedance of load-bearing capacity, then there you should use residual strength. Instability of foundation, again residual. Settlement and differential settlement of structure, there is a discussion about it, Annex C, and lateral spreading should be all considered. Again, Annex C provides some methods. Liquefaction remediation, I'm not going through it. There is a good section on it, section 7.3, that says how to do ground improvement and how to assess it as acceptable and use of piles and what we should think about in piles. Settlement of soil under cyclic loading only for moderate and seismicity, high seismicity classes. There is more information compared to 2004 version. Susceptibility of unsaturated loose coarse-grained soil can be, and densification can be evaluated. Should be evaluated. There is an Annex C for it. Settlement of insaturated coarse-grained soil due to dissipation of excess pore pressure, again due to earthquake, should be considered. Again, Annex C has a section on it. And settlement of soft, fine-grained soil due to cyclic degradation, again, should be considered due to dissipation of induced pore pressure. Finally, densification and settlement potential of soil may be evaluated with appropriate cyclic laboratory test. Just to give you a flavor of Annex C, there is, for example, free field settlements in saturated soil based on the volumetric strain and the summation over depth, and different methodologies for evaluating this epsilon V based on safety factor against liquefaction, based on CPT, based on SPT. These are from the literature. They are all basically taken from available literature. For settlement under building, also how much displacement based on some formulas available, again, informative, and with some curves all included. And for lateral spreading, the same. An equation is basically copied from the most recent studies. And these, again, all informative. Finally, site response analysis. The site response analysis, there is a good section about it in part 1. So what is actually in part 5 is mentioned. It says when relevant conditions apply. Relevant in part 1 means, for example, the conditions is such that it's not covered by Eurocode part 1. So then we are expected to perform, or we are allowed to perform, site response analysis. Then we could use that to get the time histories needed for retaining walls underground structures. Soil structure interaction, they could be done from GRA, ground response analysis. And of course, using, for example, the conventional total stress method, which, for example, with all the principles of damping, shear modulus reduction, and all that. And one is allowed also to perform ground response analysis based on effective stress methods, nonlinear constitutive method accounting for volumetric deviating methods. So both methods, rigorous, are possible, but provided that the conditions are there. So this is a little bit new in the current version. Thank you for your attention.
Thank you very much, Professor Kaynia, for your interesting presentation and for giving us such an overview what is part of slope stability and liquefaction. And if you allow, I will pass over to the question part. We have one question from Professor Kostas Georgopoulos from Kingston University of London. Professor Georgopoulos asks, with the force-based analysis, How has the latest formula calculating the accelerations for slopes in P5 changed the topography amplification factors in P1?
Yeah, the topographic amplification already is included in the definition of the accelerations. In part 1, it has been moved from previously part 5 as informative. Now the whole amplification is now included as part of hazard. So when you have the acceleration and all that determined from part 1, then there is no additional amplification or changes for topographic. If this is the question, if I understood it correctly.
I believe yes, Professor Georgopoulos. Was the answer clear for you?
Good morning to all. No, I mean, these topographic amplification factors, which are the old factors in part 1 that have been used for ages, are mainly empirical, I would have thought. So now with the new research on calculating the accelerations for slopes, I was wondering whether you had a look at them again to see whether you should change them.
Ah, I see. No, we did not go into that detail actually. So if a specific case, I can imagine, I cannot say for sure, if a specific case actually warrants a careful evaluation of that, because we have the displacement-based approach available. So one could do the analysis for good reasons. So no, back to the question, there is no new specific study done by our group for that factor. But the door is open to do a specific study that accounts for everything in a slope, including all the nonlinearities as we discussed.
Thank you very much, Amir.
May I add a comment on this, a comment to the comment?
Sure, please.
These problems have been discussed in the committee, both for the amplification factor due to topography and to basin effects. And it has been concluded after the discussion that what we have now is not mature enough to put it in the code. It will be probably in the next version because the maturity is not so good for the moment. We know that probably it is not 100% fitting the new discoveries that we have, but the maturity is still not at the level that could be used in the code.
Thank you very much, Kyriazi.
Thank you also for this intervention. One more question, namely from Jean-François Semblat from the Institut Polytechnique de Paris. Mr. Semblat is asking if how strongly heterogeneous profiles are defined, for example, the velocity gradient.
Yeah, the way it is, of course, this is a subjective thing. We have a note saying that by heterogeneity, we mean roughly factor of 3 in shear wave velocity, in stiffness, not shear wave velocity, in stiffness. So this is rough. When there is a contrast of more than 3, it is considered heterogeneous, very high level definition of that. The rest is to the judgment of the user, of the designer.
Okay, Mr. Semblat, was this clear?
Yeah, thank you very much.
Then one more question from Cyril Gomez from Fugro, France. So I will send the question over to Professor Kaynia. It's about the effective stress introduced on the new generation of Eurocode 8, while liquefaction assessment still considers the classical methodology. Does the new generation of Eurocode 8 allow to perform the liquefaction analysis using also the GRA in effective stress, so estimation of excess of pore water pressure with time?
The preferred approach is, of course, because of the long history for it, and because it has many elements, is of course the empirical CPT, SPT, and others. However, under certain conditions, as you have noticed, when the conditions are there, not necessarily, I don't think that it has been closed. I cannot say for sure, seeing somewhere, Alan can correct me, please, absolutely closing it. However, when it opens up the possibility of using lab testing for some cases, that means that it's, if the justification is there, it should be possible to do rigorous effective stress analysis, especially, of course, when it is a performance-based with a structure or other conditions there that requires that. So this is as far as I can say, but I cannot say for sure. If Alan, you want to add something.
No, first of all, we did not rule out the possibility of using lab tests. We do not recommend them because for all the reasons that Amir mentioned. But if you make your liquefaction assessment with a nonlinear site response analysis and so on, you must realize that you have a lot of uncertainties. First, in the measurement of the parameters, we just talked about it, but also with the constitutive models, the numerical analysis, and so on. So really, keep in mind that Eurocode 8 is mainly developed for ordinary structures. Let's say 80% of what you have in practice. So we cannot recommend using nonlinear time histories with a two-phase model and so on. But it's not really forbidden.
Yeah.
Thank you very much. Was the answer explicit enough for you, Ms. Gomez? Okay, thank you very much. I'm just checking the chat. And if you allow, I would address also one question from my side. It's regarding the slope stability. And the question, as far as I understand, I would just want you to confirm that if possible. What if you have a multi-layer slope? So we have many layers of soil, different types. It often comes to that. I know it's an exception, but it's often in practice. What happens regarding the approach we are allowed to do? Namely, we have the force-based display or displacement-based approach. I would say we are forced to go to the displacement force approach. If soil layers are different and we have this more complex situation.
Yeah, it's the same discussion. Actually, I mean, if the method is such that still allows, if you want, with this key factor and others, even if you have, because no soil medium is perfectly homogeneous, perfect. So it is a condition, it's always there. So I think with some judgment, we could still use the force-based approach. And these displacements are not absolutely for very, very idealized cases. They have been adapted a little bit so that certain non-homogeneity can be accounted for. So I would still dare to use them. But as you said correctly, if it is absolutely one considers necessary to use it, the door is again open for it. But I think personally, there is enough flexibility and some conservatism when we adopted these key factors that was used also the beta that account for certain heterogeneity, in my opinion.
Can I contribute to this discussion? Just the force-based approaches are really an immediate extension of the approaches that we use for static analysis. So in fact, if we are able to analyze a layered slope problem statically to find its safety under static conditions, then in principle, we should be able to extend that to the force-based approach under seismic conditions. As for the problem would be the validity of the key values, but I believe that the way they've been derived is sufficiently general, and the dispersion in the key values is not really related to the inhomogeneity of the soil, rather to the variability of the seismic action. So I think that they could be applied also for a layered soil.
Okay, thank you. I had in mind, for example, if you are on a bend of a river, yes, and we have naturally and normally all sorts of layers. We can have layers of soil where the static approach may apply, but we also may have high deformability for a layer along the depth of a possible foundation influence area. And then the question arises, what are we still allowed to do the, let's say, simplified approach or not? But I understood your opinion, and also the fact that the factors that apply to this calculation are also sought for unhomogeneous soil structures.
We did not perform very extensive study, but the conservatism that is there and the methods that have been used at the end to come up with these factors actually cover a large portion of complicated cases. So this is overall, I think, applies. You could take a very special case and analyze it, and these factors might not apply, but these are, like, again, back to the user.
Yes.
In our opinion, it's good enough for many, many cases.
Thank you very much for this good news. And if I may still have, yes, we still have a little time. I would have one more and last question regarding the soils that are sensitive to liquefaction. I don't know, just as a feeling, in high seismic areas, or can we take this possibility to build constructions on soil that are subjected to liquefaction? I know there are stages of liquefaction, yes, but still, if we have a high seismic area, as far as I knew until now, this was actually something we should not do at any point or under any conditions.
Yes, actually, yeah, it is allowed. It's more specific now. As you remember, yes. This slide, low seismic action, moderate seismic action, even high seismic action. Potential consequences should be evaluated. Things become more complicated, of course, when you go to high seismicity. So all these things with respect to, for example, bearing capacity, using residual strength, residual strength is so low, yes. But if you still have bearing capacity and all the issues here, for example, instability, settlement, they all, as you go to more and more severe conditions, they become more difficult to satisfy. And of course, at the end, liquefaction remediation, if none of these work, ground improvement is now has come a long way. And so it, again, it opens up the possibility for doing it rather than saying, indiscriminately saying that, yeah, yes. Just leave the site. Yes.
Okay. So there is a confidence there that we may deal with that also. Thank you very much.
At the end of the day, it is the engineer, that has, because these are general guidelines. We should realize that we are not completely taking it from them. It's the purpose of the code is to give actually that flexibility to keep it and give more guidance as to what to watch out and what to avoid.
Thank you very much for your kind answers, and thank you very much again for the presentation today.
You're welcome.
And I would suggest my colleague, Professor Butenweg, to take over the next webinar part. Thank you.